Okay, let's dive into this. If you've ever worked with Kubernetes, you've probably banged your head against the wall when it comes to networking. It can be a real headache, right? Well, today we're going to clear things up by demystifying one of the most essential pieces of the puzzle, the Kubernetes service. So, to really get what a service does, you got to start with a problem it's built to solve. Imagine you've got your front end and your back end apps running in pods. They need to talk to each other. But how? It's kind of like trying to send a letter to a friend who moves to a new apartment every single day. How would that letter ever find them?
And that gets us to the core of the issue. Pods are what we call ephemeral. They're literally designed to be temporary, disposable things. You shouldn't think of a pod as a permanent home. Nope. It's more like a temporary P.O. box that gets thrown away and replaced at the drop of a hat.
Let's actually walk through what this looks like in the real world. So your front-end V1 pod is up and running, humming along at its IP address, but then, oops, something goes wrong. A bug, it runs out of memory, whatever, and it crashes. Kubernetes, like the good manager it is, sees this and instantly spins up a replacement. But here's the kicker. That new pod, front-end V2, it gets a brand new, completely different IP address. The old one, it's gone. Vanished. Forever. And this brings us right to the million-dollar question. If you're the back end, how in the world are you supposed to reliably find the front end? You can't just hard code an IP address because you know for a fact it's going to change. It makes any kind of stable, direct communication pretty much impossible. And this is where our hero of the story makes its grand entrance, the Kubernetes service. What a service does is it solves this exact problem. It gives you a single, stable, permanent address that never changes. Think of it as a reliable front door for a whole group of pods that are constantly moving around in the background. This table here, it breaks down the difference perfectly. A pod is a real thing. It's actually running your code, using CPU and memory. It has a real IP address. A service, on the other hand, it's just a logical idea, an abstraction. It doesn't run any code itself. Its one and only job is to provide that stable, virtual IP so other things can communicate without chaos. So how does the service know which pods it's supposed to be the front door for? Well, it uses this really simple but super powerful trick called a label selector. All you do is stick a little tag, we call it a label, like app front end, onto all your front end pods. Then you just tell the service, hey, look for any pod with that exact label. That's it. It's basically a matching game.
Okay, this is where we get to the really juicy part, what I like to call the label selector myth. See, most people think they understand how this works for day-to-day network traffic, but the reality is a little bit different, and honestly, a lot more clever. Just think about this for a second. Let's say a network request comes into the service. To figure out where to send it, does the service really, for every single packet, have to scan every single pod in the entire cluster just to find one with a matching label? I mean, what if you have thousands of pods?
Yeah, no way, absolutely not. That would be a total performance nightmare. Your network would just grind to a halt. Remember, Kubernetes is built for massive, massive scale, and a design like that just wouldn't fly. There has to be a smarter way. And there is a much smarter way. The real magic behind how a service works so fast isn't the label selector, not at runtime anyway. It's a whole other object called an endpoint slice. This little thing is the real key to efficient, lightning-fast traffic routing.
So here's the punchline, the big myth we're busting today. The label selector, its job is done at the very beginning, during the initial setup. It is absolutely not used for routing live network traffic request by request. So what the heck is an endpoint slice? Just think of it like a cheat sheet. It's a precompiled, optimized list. When you first create the service, Kubernetes uses that label selector one time to find all the matching pods. Then it takes their real, current IP addresses and puts them into this simple list, the endpoint slice. And this whole setup process, it happens in a flash, and it only happens once. You create the service, the control plane does a quick, one-time scan with the selector. It builds the endpoint slice list with all the right IPs, and from that moment on, every single routing decision is made by just glancing at this super fast list. No more searching, no more scanning.
Okay, but wait, you might be wondering, what happens when a pod crashes and gets a new IP? How does that cheat sheet, the endpoint slice, stay up to date? Well, this is where the real machinery behind the magic kicks in.
It's actually a really beautiful system. At the very top, you've got the control plane. It's like the brain of the whole cluster. It's constantly watching for any changes to pods. A pod gets created, deleted, its IP changes. The control plane sees it and immediately updates that endpoint slice list. Then, on every single computer in your cluster, what we call a node, there's a little process running called kubeproxy. Its only job is to watch that list, and whenever it changes, reprogram the local networking rules on that machine. It's a constant, automatic, self-healing process.
So why go through all this trouble? Why this two-step process? Because separating these two jobs, using selectors for the initial setup and a simple list for the actual traffic, is precisely what makes Kubernetes networking so incredibly powerful and scalable.
All right, let's wrap this up. What are the big takeaways? First, efficiency. It is so much faster to look up an IP in a simple list than it is to do a cluster-wide search for every single request. Second, scalability. Pods can pop in and out of existence all day long, and your network performance doesn't even flinch. And finally, decoupling. This is huge. Your apps only need to know about one stable service address, and they can remain blissfully unaware of the chaos of pods coming and going behind the scenes.
All right, so we have totally nailed how services talk to each other inside the cluster. But that leaves one big glaring question, doesn't it? We've got this stable internal address, which is fantastic, but how does a user out on the public internet actually get their traffic into our cluster to hit that service in the first place? Well, that is a whole other can of worms and a story for another explainer.